Okay, so let's try to integrate this algebraic bad boy up here. So this, I don't think there's much we can do with this since there's an odd power in the denominator, and it's also it's weird, right? Because you can factor it into an irreducible quartic and a first degree polynomial, a linear term. But let's go ahead and do that and see how it goes for us. Because the answer, I can tell you this already, it's going to be pretty bad. But yeah. Okay, so the bottom, x to the fifth plus 1, you're able to factor it. And I'll show you how we can do that. Since we know that just by trial and error, if you plug in -1 to x, then you found a root. So therefore, our root can be represented by this linear polynomial right here, but you also want to factor it into two polynomials. So here's how we do that. Let's just use synthetic division, but there's many better ways to do this. So our root is at -1, right? And then we'll just use synthetic division. Fifth degree, we have a coefficient of 1. Fourth degree, 0. Third degree, second degree, linear, and then a 1 again at the very end. So we bring this down to 1, multiply this guy, you get a -1. Bring this down to -1, multiply this guy, it's a 1. Bring this down into 1, multiply this guy to -1. And the pattern repeats, right? So eventually you're going to be multiplying a -1 into here, and the remainder will be 0. So therefore, you get a quartic polynomial with these coefficients. So here we can break this up. We can break the denominator up into x plus 1, which represents our first root, and then this quartic polynomial with these coefficients. So this would be 1 times x to the fourth minus x to the third plus x squared minus x plus just 1. Not so bad so far, but we're not even close to being finished. All right, let's get rid of our work. So here, our end goal would really to be just to factor this thing into as many linear terms as possible that represent all of the roots of this polynomial, and then irreducible quadratics that represent the complex roots. So how do we factor this? This doesn't have any real roots. If you just think about it, right? So how do we factor this guy into two quadratics? Well, and do we want to even do that yet? Since here, the only reasonable step that comes next is a partial fraction decomposition. In fact, let's do a partial fractions right now, and then we can move on to factoring this next boy over here into some irreducible quadratics. So here's what we're going to do. Let's do our first partial fraction decomposition. So we want this rational expression right here with x plus 1 times this quartic in the denominator to be split into two fractions. One with denominator x plus 1 and one with denominator this right here. So you got x to the fourth minus x cubed plus x squared minus x plus 1. And then we want polynomials on top with 1 degree less than the denominator. So on top of here, this would just be a constant numerator. Then here it would be a cubic numerator. So here's how we do this. We write bx cubed plus cx squared plus dx plus e. So now let's solve for what these coefficients would be. If we multiply the denominator on the right hand side and the left hand side, we end up getting that this cancels out, so you just end up with the 1. On top, you get a times x plus 1 cancels out with x plus 1, and you're left with a times this thing right here. So you get a times this, which is x to the fourth minus x cubed plus x squared minus x plus 1, right? Then we have an addition. This second term right here, this quartic cancels out with that quartic, so you're just left with the linear. So this numerator is still here. You have bx cubed plus cx squared plus dx plus e. Now you're multiplying by binomial x plus 1. Okay, so let's distribute it. Let's expand this guy out and then group these by group the terms by the degree of their exponent, because that way we can now set up a system of equations. So this is equal to, just distribute the a. I'm going to write this all in black. Ax to the fourth minus ax to the third plus ax squared minus ax plus 1. Here we have 2. So to think about multiplying by x plus 1, basically we want to distribute twice. We want to multiply this polynomial by x and then this polynomial by 1. So basically we're going to be raising each of the powers, each of the degrees of each of the terms in this polynomial by 1 when we're multiplying by x, and then add just the original copy when we multiply by 1. So here we would have bx to the fourth power plus cx to the third power plus dx squared plus ex. And I realize I'm running out of room. And then now to multiply by add 1, we just copy the original down. Bx cubed plus cx squared plus dx plus e. So now let's group these terms by the degree of their exponent. So we have 2 fourth degrees. We got one right here, one right here. We got 1 in terms of third degree polynomials. We got 1, we got 2, and we got 3. For the second degree polynomials, I'm pretty sure we have 4, right? We have 1, 2, 3. Wait, sorry, we have 3. And then for the linear ones, I'm pretty sure we have 3 again. Yeah, we have 1, and then 2, and then 3. And then for the constants we just have what kind of underline have I not used yet? 1, and then 2. So yeah, now let's group all of these guys. So let's rewrite the 1 as well. So 1 must equal, in terms of fourth degrees, we have ax to the fourth and bx to the fourth. So we can group those together like this. A plus b, and then times x to the fourth. In terms of third degree polynomials, right, we have a negative a here, a plus c here, and then plus b. So we got a plus b plus negative a plus b plus c, and then times x to the third power. Next up, we have the second degree terms. We have a, we have a d, and we have a c. So we'll write this as a c d. So you got plus a plus c plus d times x squared. And then we have our linear terms, which is we have a, d, we have our linear terms. So we have a, and we have d, and we have e. So we'll write this as plus a plus d plus e, and then just times x by itself, and then we just group the constant terms, of which we have 2. We have 1 and we have e, so we have e plus 1. If I'm not wrong, sorry, no, this is not 1, that would actually be an a, because we distributed the a inside, so we actually have e plus, well, let's rewrite this as a plus e. Alright, so now let's set up a system. Let's see on the left-hand side, we don't have all of the coefficients that isn't for the constant term, all evaluate to 0. So that should correspond to what we have on the right-hand side. So that means this, and this, because they all have x's attached, whereas nothing on the left-hand side has x's attached, should all evaluate to 0. So our system goes like this. We have a plus b being equal to 0, negative a plus b plus c being equal to 0, a plus c plus d being equal to 0, and then this should be a negative a. We have negative a plus d plus e being equal to 0, and then we have a plus e being equal to 1, because this is our only constant term, similar to on the left-hand side. A plus e should equal to 1. Okay, so I see the first thing we can do, we can work our way from the bottom up. Since a plus e equals 1, this implies that if we plug that's not how this works. So how should we do this? So let's work our way from the top down, actually. So here, if you just isolate, say, a, we get a equals to negative b, right? So just plug in negative b for wherever a is here. We get b plus c, right? Because negative cancels out. We got 2b plus c equals to 0. Therefore, 2b plus c equals to 0. Right, and I should keep this the same. Okay. Next, what we can do is we see that 2c is equal to negative 2b, right? So keep the c here is equal to negative 2b. We can write this. Can we write this all in terms of a? So we have negative a. This would be minus a. Then plus c. Sorry. Give me 1 second. I want to see if we can do something smart here. In fact, why don't we add some of these guys to have coefficients cancel out? That's basically what we did here. We added these two, right? So adding these first two gives us this new condition. A and A cancel out. We got 2b equals to c equals to negative c, or 2b equals to c. So let's go down here first, right? If we add these, we get that 2e is equal to d. Okay, so we can plug 2e in here, and then we can plug 2b into here. This is completely improvised, so we'll see what we can do. But 2b into where c is, we get negative a plus b plus 2b gives you plus 3b equals to 0. So basically, 3b is equal to negative a. Not negative a, because this is already negative, so we don't need to flip anything around. Because of this property right here, we can do, so we now plug 3b into here, so we get 3b plus b is equal to 0. I'm pretty sure I did something wrong. B is most certainly not equal to 0. So let's see what we can do. Start on this partial fraction decomposition. Why don't we eliminate all the a's from this equation? Sorry. So what we can do here is, well, originally I was going to do this, but we can write that a is equal to 1 minus e. Therefore, plugging 1 minus e into here, into wherever you see an a, we get negative e, which is plus e. So negative 1 plus e plus D plus E is equal to 0. So move stuff around, and you get that 2E plus D is equal to 1. Because the original way I would have done it was just to use the cover-up method to solve for A, since you see that here A is just by itself on top of a linear term, but it's okay. We're going to try to do this the system's way. And similarly here, isolate A, and get A equals negative B. Plug negative B into here, we get 2B plus C equals to 0. And then here, whatever we want to do, we can C plus D. In fact, we can write this in terms of all B's, I think. No, not B. 2B plus C, and then negative B minus 2B. Yeah, let's just let's put in a negative B here, negative B, and then if you move this over, we get negative C equals negative 2B. So we got a negative B here minus 2B plus D. All right, so a negative B minus 2B, that's negative 3B plus D, right, is equal to 0. So I think we have our system of new variables that we can use. In fact, you can make some other inequalities here too. Like if we were to take this and set it equal to that, since they're both equal to A, we would have 1 minus E is equal to negative B, right? Which is also add B and add E, you get 1 plus B is equal to E. So we get 1 plus B is equal to E. Now what can we do? C, can we write that in terms of B? I'm pretty sure this is what I did earlier, but 2B equal to negative C, right? Well, that wouldn't help us since we want B in terms of D to plug in here. And then we can use this property up here since it's going to be an equation of B and D. So, in fact, what we can do is isolate D here. Get D is equal to 3B, right? So, whatever we see here, we can write 2E plus 3B, since D is equal to 3B, is equal to 1. Okay. So, that's what we've gotten so far. Now we want to take advantage of this boy. How do we do that? We can use... Okay, in fact, what we can do here is isolate the 1, so we know that E minus B is equal to 1. Therefore, plug in E minus B into here, we get 2E plus 3B is equal to E minus B. And then add B on both sides and subtract E on both sides, you get E plus 4B is equal to 0. This is very, very interesting. This is the first time I've done partial fractions for this guy this way. I'm pretty sure there is a better way to do it. I've taken forever to do this, but yeah, this is just improvised. This is just improvised. Okay, so what do we have now? We have another equation in terms of E and B. In fact, we have another one here. We can use this guy right here. So I'm going to say we add these two. Well, no, we subtract these two. And then we solve for B. So, in fact, E is equal to, if you add just B on both sides, you get B plus 1. And then here you get, if you subtract 4B on both sides, you get E is equal to negative 4B. Therefore, negative 4B is equal to B plus 1. Therefore, adding b on both sides, subtracting 1, 5b is equal to negative 1. Therefore, b is equal to negative 1 over 5. That is our first answer. In fact, let's keep track of all of this up here. So right now we have b is equal to negative 1 over 5. Okay, so that's all we need for here. Let's solve for e using this. And then you can also solve for a, but let's do e first. So if you get rid of this, you see that we already have e isolated in an equation up here. Plug in negative 1/5 here, you get e is equal to negative 1/5 plus 1, which is equal to negative, oh no, not negative, just 4/5. So we get e is equal to 4/5. And there is a pattern here, but we'll see as we go. Okay, so now we have e and b solved for. We don't no longer need any of this. And this either. So, since we have e, we can also just solve straight for a, right? So plug in 4/5 into here, we get a is equal to 1 minus 4/5, which is just equal to 1/5. So we get a is equal to 1/5. Okay, now let's take a look at, so we no longer need any of this term, any of these with in terms of a. This is very, very brute force, so I'm not keeping track. I'm not doing this in any systemic way. Let's solve for d. We got e is equal to 4/5. Wait, what is this equal to? We plugged in 2e for negative a plus negative a. Okay, this is my bad. But we know that negative a is 1/5. So I'll just take a look at these root equations, right? Then we have the negative sign out here. Plus d and plus e, which is 4/5, is equal to 0. So we can do, you can add 1/5 on both sides and subtract 4/5. Adding 1/5, you get d plus 4/5 is equal to 1/5. Subtracting 4/5, you get d is equal to negative 3/5. So this would be equal to negative 3/5. Okay, lastly, let's just solve for c. C isn't all that bad. We can get rid of all of this basically. But plugging in a, we get 1/5. And then plus c, we don't know yet. And then plus d, which is negative 3/5, is equal to 0. Our first step would be to add 3/5 on both sides. 1/5 plus c is now equal to 3/5. Subtracting 1/5 on both sides, you get 3/5 minus 1/5, 2/5. So therefore, c is equal to 2 over 5. So just write that down here, 2 over 5. There we go. So now we can get rid of all of our partial fraction work. And by the way, we're going to need to do something very similar later on, but it's not going to be as nice as this. But yeah, we have all of our coefficients, and therefore can rewrite all of this. So this integral right here is equal to, in fact, let's split the integral. First, we have this term, a over 1 x plus 1. We have 1/5. We can bring the 1/5 outside using the linearity of the integral. So you get 1/5 times the integral of, this just becomes 1 over x plus 1 with respect to x. Okay, next we add, and then the next integral is this big boy right here. So we want to, if it comes like this, we want to find a common factor among all of these coefficients right here to factor out to the front of the integral. So we are done with a. We just see this, right? What can we factor out? There's a 1/5 in common, a fifth in the denominator. So in fact, what we can do is just factor out a 1/5. So 1/5 times the integral of this fraction. But now that we factor out the 1/5, all we need is whatever's in the numerator. B is just negative, so you get negative x cubed. And then C is just now 2 after factoring out the 1/5, so you get 2x squared. D is negative 3x. Yeah, and then E is just 4 after factoring out the 1/5, so we get 4. And then our denominator is just this. So this is now in an integratable form. So in fact, what we can do is we can make a note up here. Let's let 1/5 times the integral of 1 over x plus 1 with respect to x equal to I1, right? So now ignore that. All we're dealing with here is this. So let's get rid of all this. Well, okay, you know what? Let's draw a border for now because everything on this board is going to be temporary. So how do we manipulate this? Well, firstly, this x to the cube, x cubed in the numerator, it has a negative, and since it's the highest degree term, we want to factor out the negative. So what we can do is we can make this negative 1/5 times the integral of, and then now the x third is no longer negative, but then all of the signs flip polarity, so this would be minus 2 times x squared plus 3x minus 4 over x to the 4th minus x cubed plus x squared minus x plus 1 dx. Okay, so now what can we do? So this guy right here, since there's a cubic on top and a quadratic on the bottom, and all of the terms are indeed present, why don't we manipulate this, like multiply something in on the top to make it so that we can split this fraction into 2, where one fraction is where one of the numerators is the derivative of the bottom, so we can use a natural log. So how do we do that? Let's just take a look at this first term right here, x to the 4th. So if we take a look at x to the 4th, what we see is that the derivative of x to the 4th is 4x to the 3rd. So in order for us to have that coefficient, we need to multiply by 4 on top, but that also means we have to divide by 4. So dividing by 4, let's just do that. Dividing 1/5 by 4 gives you negative 1 over 20. And you have the integral of, then you have to multiply 4 in on top. You get 4x to the 3rd minus 4 times 2 is 8, x squared. 3 times 4 is 12x. And then 4 times 4 is 16. And then the denominator stays the same. Dx. Okay, so what next? Now we see that negative, in fact, we can keep doing this down here. So let's write this down in another row. So the denominator will still be x to the 4th minus x to the x cubed plus x squared minus x plus 1. But in the top now, you can see that what we can do is that this is already the derivative of that. Alright, so we can just leave that there. The derivative of negative x cubed is negative 3x squared. So what you can do with this is you can split the negative 8x squared into a negative 3x squared. Let's write x squared in black. And a negative 5x squared. So we'll put that down later. Now for this, the derivative of x squared is just 2x. So if we want to make a 2x out of this, we can leave a 2x here, but then we need to we're going to split this into 2 and 10. We need the 10x later. Okay, now for this last one. The derivative of negative x is just negative 1. So we're going to leave a negative 1 here, and then we're going to add on the rest later. Let's close this integral for now. Right. Okay. And we're going to do all the compensation, right? We have to compensate for the fact that we added and subtracted coefficients for the variables right here. So what we're going to do is we're going to split this integral into 2 first, and then compensate here on the next integral. So we got minus 1 over 20 integral. And the bottom still has to stay the same for the compensation to be accurate. Okay, so on top, what we did here, we now have a negative 5x squared that needs to be dealt with, so we can move that here. In the linear term, we originally had 12x, now we have 2x, so we still have a 10x squared that we need to deal with. Not squared. And then here we had a negative 16, here we have a negative 1. We still have a negative 15 to deal with. So now this is actually you can immediately integrate this since the denominator is u, then the numerator times dx is du, and that just gives you natural log. So let's write this down as a different, let's just keep note of this up here, and then we'll deal with this by itself. So we can let the coefficient, this is just negative 1 over 20 times the integral of, got 4x cubed minus 3x squared plus 2x minus 1 is equal to x to the 4th minus x cubed plus x squared minus x plus 1. Dx equal to I2. All right, and at the end, we're going to add all these up since all we're doing is we're just taking off terms and dealing with the next most difficult one. Okay, for this term, you can see that there's a simplification to be made. Since the top, everything has a common factor of 5, of negative 5, because we can factor the negative, and the bottom also has a negative 5 in it too. So after making that simplification, we don't want an equal sign here. We just start a new one. So after this simplification, we divide the top by negative 5, divide the bottom by negative 5. The negative, dividing 20 by negative 5, we get negative 4, but the negative and the negative cancel out. So you just get 1 over 4. 1 over 4 times the integral of, dividing the top by negative 5, we just get, well, in fact, let's write down the denominator first, since it's going to be a lot longer. X to the 4th minus x cubed plus x squared minus x plus 1. Dx. Okay, in the top, we're going to divide everything by negative 5. We get just x squared plus 10 divided by negative 5. You get minus 2x. And then a negative 15 on top, divide that by 2. No, sorry, divide that by negative 5. You get just positive 3. There we go. So that's our new guy to deal with. You can't really do anything with this now, so we might as well try to factor the denominator and then do partial fractions. So, yeah, okay. Now to factor the denominator, there's a cool trick where we leverage a little bit of a symmetrical look. So we're gonna get rid of all of this work since we don't need it. We have it all taken care of. And let's do a factorization. So here, we're trying to factor the denominator and then do partial fractions. So our next task to accomplish is to factor x to the 4th minus x cubed plus x squared minus x plus 1. So from here, we can actually factor out an x squared from everything. That would make this 1 over x, that would make this x squared minus x plus 1 minus 1 over x plus 1 over x squared. And that gives you a kind of a nice symmetry to work with. I'll show you. So we have x squared minus x plus 1, and then minus 1 over x plus 1 over x squared. So now we have a nice symmetry, right? In fact, here, there's a square. There's a perfect square hidden in here somewhere. If you take x squared plus 1 plus 1 over x squared, you can see that that's actually almost a perfect square. You just gotta complete the square by adding 1 and subtracting 1 in the middle term. So we got x squared, and then x squared, we're gonna write this out front here. And then now this is gonna be plus 2, so that it's a perfect square trinomial. Oh, plus 1 over x squared. I'm gonna write down the linear, guys. 2, we got x minus x minus 1 over x. And then, so that's all the terms, but remember, we added 1 here. Now we have to subtract 1 again, so we get minus 1. So, now, this is a perfect square trinomial. We can rewrite it as just a simple perfect square. We got x plus 1 over x squared. Here, we can factor out a negative in the linear terms. So we have a minus x plus 1 over x, right? And then can't do much with the constant term, so we can just leave it there. If we just make a substitution so it's easier to see, we can let t be equal to x. No, not t. Let's use a different variable. Yeah, t is just too nice to be used here. Let's let y equal to x plus 1 over x, right? In this case here, we see that the x squared would stay. We're not going to replace that. But inside of the parentheses, we can see that there's a y squared minus y minus 1. Now, in fact, what you can do here is you can complete the square, right? Of course, you can use the quadratic formula and then rewrite this in factored form, but this is a really nice binomial. I want to derive this the proper way. To complete the square for y squared minus y, we want a plus 1/4. And then we can do whatever the hell we want with the 1. So x squared, y squared minus y, and then to complete the square, we add 1/4. But to be able to add 1/4, we also have to subtract 1/4 immediately after. There is always going to be a negative 1 here. If you subtract 1/4 from that, you get negative 5 over 4. So now you can rewrite this as a perfect square. This is a perfect square trinomial. You can rewrite this as a binomial squared. So we get x squared, and then we have y minus 1/2 squared, right? And then you still have to subtract 5 over 4. So what do? If you want to factor this into two binomials? Well, since you're subtracting and there's a constant here, what you can do is rewrite that constant as a square of something and then factor this as difference of squares. So the negative sign stays, but for this to be something squared, you want to take the square root of both the top and the bottom. Square root of 5, can't really do anything with that. It's just root 5. Then the bottom, square root of 4, is 2. And now this is squared. Let's take this up here. So to factor this bad boy right here, rewrite this as difference of squared. So we can keep the x squared, right? But we have this, whatever's inside of here, right? So we can call this just y minus 1/2. First, you want to subtract whatever's in here, and then you want to add. So let's subtract first. So we subtract root 5 over 2, right? And the next factor, you want to add it. So we've got y minus 1 over 2 plus root 5 over 2. So now we got x squared, and then y minus. So you can combine the fractions, and this becomes 1 plus root 5 over 2. And then multiply this by 1. And then you can factor out we don't need to factor out anything. Let's just leave it positive. And then in here, negative 1 plus root 5 over 2. And in fact, what these two numbers are variance of the golden ratio. Negative 1 plus root 5 over 2 is just negative phi, right? And then y plus negative 1 plus root 5 over 2 is just 1 over 5. So we can write it as such. Okay, what's next? You see that there's two x's here and there's two binomials here. Multiply the x into the binomials and you're done. So, in fact, let's do that first. So, multiplying the x in, we get x, y, minus 5 times x. Right, and then here we get xy, and then plus 1 over 5 times x. Okay, but now we want everything written in terms of x, so what did we set y as? X plus 1 over x. So the x stays, and then we have an x plus 1 over x wherever the y used to be. Then x times, I'm running out of room again, plus 1 over 5x, and then close. Okay, distributing the x, we get an x squared plus 1. So, in fact, we get an x squared, right? And then we can actually move the 1 to the back of this now trinomial. So we get a minus 5x, and then plus 1. X times 1 over x is 1. Same thing happens in this other trinomial right here. We get x squared plus 1 over 5x, and then x times 1 over x is just plus 1. So you've now factored this into two trinomials, two quadratic trinomials, as we said earlier. So this thing doesn't have any real roots, but the complex roots can be written. You can group the complex roots, right? Since they gotta be conjugates of each other, and in a quadratic, if it only has complex roots, then they're going to be conjugates of each other. So basically what you do is you group the conjugates, multiply them together, so whatever the conjugates are, and then that gives you a nice quadratic for each pair of conjugates, that come from the complex roots of that. That is what we're dealing with. So in fact, this right here, we can just replace the denominator with this this product of trinomials. So the bottom is right as x squared minus phi x plus 1 times x squared plus 1 over phi x plus 1. And by the way, because these are complex, because they only have complex roots, because they are complex conjugates, right? These are irreducible quadratics. You can't write them in terms of linear terms unless you want a complex number in as the constant term in your linear polynomial. Right here. So we wrote that down, and then now we just have the numerator left to deal with. We just write that up there. No need for anything special regarding this. Can't factor that either. Notice, because to complete the square, you get x squared minus 2x plus 1. Write that as a perfect square, but you're still adding another thing. Sum of squares, you can't factor. Okay. dx. So we're done with this part, which is typically the place where it's very difficult to get past, since this first step and this completing the square is not very immediately evident. Okay, let's get rid of this, and then let's deal with the partial fractions of this guy. So earlier during our partial fractions, in fact, because I once did this in one big whiteboard before, I had to control which variables I used. Let's make a list of used variables. So, can't use, phi is a number, so we already can't use that. We already used x, of course, and of course, this is just going to be for substitutions and partial fraction, right? Just to make sure we don't use the ones we already used. We used y for the factoring. We used A, B, C, D, and E for the partial fractions. And also, I, in because these are just our different. These are just our different like setup integrals. We're gonna integrate them all at the very end, all together by making a big substitution. Well, not one big substitution, multiple big substitutions, since each of these terms require different substitutions. Well, after we break this up, of course, to actually be able to be integrated. Okay, so that's that. Let's do this is basically the biggest part of all of this. Let's do a partial fraction decomposition for that. So we have x squared minus 2x plus 3 over x squared minus 5x plus 1 times x squared plus 1 over 5x plus 1. I want this to be equal to, since it's two quadratics, then you want to write the quadratics on the bottom. You got x squared minus 5x plus 1, and then x squared plus 1 over 5x plus 1. Now this is going to be pretty rigorous. Well, not even rigorous. This is just going to be pretty difficult. And because there's quadratics on the bottom, we now want a polynomial with 1 degree less on top. So we want linears on top. We used A, B, C, D, E. Let's use, it's going to be pretty obvious, just the next set of letters in our alphabet. We can't really do anything, right? So AX, no, I just said we're not going to be using that. So what comes after? What comes after E? We got fx plus g, and then hx plus I, right? But let's not use the I since we're representing them using integrals. So to our list, in fact, now we can add f, g, h, j. So that gives you kind of idea of the complexity of taking this antiderivative. And by the way, all of this came from this little innocent looking guy over here. Anyways, let's do the partial fractions now. Multiplying whatever the hell's in this denominator, that monster, into on both the left and the right hand side. On the left hand side, it cancels out with the denominator. So we now get just the numerator itself, x squared minus 2x plus 3 is equal to, in this first term, numerator stays fx plus g. But this guy cancels out with this. Now we just have this left. So we want to do x squared plus 1 over 5 x plus 1. Second term, we have hx plus j. This 1 over 5 thing cancels with this 1 over 5. We just have that left. So this is now multiplied by the trinomial x squared minus 5x plus 1. And we have nothing left to do but expand this out. Yeah. So let's write an equal sign here. fx times x squared. Let's just do this manually. fx times x squared, we get fx to the third. Fx times plus 1 over 5x. We get f over 5x squared. Then plus fx times 1 is just fx. Now time for g. G x squared plus g over 5x plus g. Next term. So hx times x squared, we get hx cubed. Hx times negative 5, we get negative h. Well, 5 is a number. So technically it would be phi hx. Yeah, let's write negative phi hx. And then remember there's x times x, that's squared. Hx times 1 is just hx. Now for the j, we just distribute that into each of the terms. Got jx squared minus phi jx plus j. There we go, no errors this time. Now let's group these all by their degree. Okay, so cubics. Right, we have 1 cubic and then 2 cubic. In terms of quadratics, we actually have 4. We have 1 quadratic here, another quadratic here, another quadratic here, and another quadratic here. In terms of linear terms, we have a 4 as well. So we have 1 here, 1 here, 1 here, and 1 here. And then finally our very nice constant terms, we only have 2. And we have this one right here and this one right here. Okay. So now let's group this and create a system of equations. So let's write an implication symbol. We got x squared minus 2x plus 3 is equal to, let's write down the cubics first. The coefficients of the cubics are f and h times x cubed. For the quadratics, we have, we'll just write it down in order. We have f over phi plus g plus, this would be minus phi h, and then minus g minus phi h, then is there a phi here? Yeah, because it's, wait, sorry, I was looking at the wrong thing. This should be this one. So we have plus j, and we factor out the x squared. Okay, now we have the linears. So the linears are f g over phi h and negative phi j in the next. And then we just have 2 constant terms, which is g and j. So we have g plus j. Done. So now we group each of these coefficients and set them equal to each other on both sides of the equation. We don't have a cubic term on the left side, so f plus h would need to be equal to 0. I'll just start by making the phi in terms of decimal, writing the phi in terms of decimal. So over phi, we get negative 1 plus root 5 over 2 f. Then, sorry, I'm not going to write this red. I'm going to keep it black for the left-hand side. Plus g minus, and then phi is just equal to 1 plus root 5 over 2 h. And then, why did I do that in red? I feel like I shouldn't. It's muscle memory at this point. 1 plus root 5 over 2h plus j. And then this would be equal to 1. Okay. Maybe I didn't make an error, but I'm going to do this in the sake, just in case I did make an error. I don't want to, I don't want this to be completely pointless. So, f plus g over phi, which is negative 1 plus root 5 over 2 times g plus h minus phi, which is 1 plus root 5 over 2 times j is equal to negative 2, which is the linear term coefficient. In fact, I'm going to write this in red. I'm going to write this in, Okay, so we're going to apply the property we did earlier. It doesn't seem like I made any errors. Okay, anyways, and there's supposed to be an f coefficient here, so I'll write that down real quick, but it wouldn't have affected anything. Okay, for this first one, we just plug in 0 where we see, for this first one, we use g plus j equals 3, g plus j equals 3. Subtract 3 on both sides, we get negative 2, on the right-hand side at least. Negative 1 plus root 5 over 2 times f minus 1 plus root 5 over 2 times h is equal to negative 2. So it doesn't appear as if I did anything wrong necessarily. We'll see. G plus j equals 3. No, okay. Now here we use f plus h equals to 0. So f plus h equals to 0. We can just ignore those two. right now let's just copy this down again. We got negative 1 plus root 5 over 2g minus 1 plus root 5 over 2j is equal to negative 2 as well. Okay, so I think our next step should be to multiply everything by 2. Right, this appears to be correct from the notes I made earlier. Okay, let's multiply everything by 2 I'm going to erase these so it doesn't clutter up the space, but I know this isn't like the best practice to erase your work, just in case you need to come back and check if you did anything wrong. But this whiteboard has limited space. I could theoretically do everything really small, but I want it to be usable. I want this video to be usable. So multiply everything by 2, we get negative 1 plus 5 plus root 5 f minus 1 plus root 5 h is equal to negative 4. Similarly, multiplying everything here by just 2, you get negative 1 plus root 5 g minus 1 plus root 5 j is equal to negative 4 as well. Now, in fact, what we can do here is we can split up the numbers and then, we can do something by distributing the variables into the numbers, seeing where that takes us. Yeah, okay, this is correct, because we're actually going to apply these properties again in just 1 second. I'm going to write this down here now, since it's getting repetitive trying to erase everything. No, in fact, let's write it here. No, let's keep it down here. Okay, so here we have negative f plus root 5 f, then minus 1 minus h minus root 5 h is equal to negative 4. Down here, we have negative g plus root 5g minus j minus root 5j is equal to negative 4. So there's nothing wrong, it's just these aren't actually equal, because after we do all the algebra, we see that, in fact, we can factor out a negative sign here between the g and the j, and we get g plus j again. So, in fact, let's keep doing the math. Wait, it's supposed to be done. So, for this top one, right, factor out a negative for f and h, so this is technically negative f plus h, negative f plus h. F plus h is 0, it's just negative 0, right? So, these two are still, just get eliminated. Here we have root 5f minus root 5h. What we can do is factor out a root 5. So factor out the root 5, and then the f plus h is still, f minus h is still there, and it's still equals to negative 4. For right here, a negative g minus j is just negative g plus j, which is negative 3. So there's a negative 3, and then the other crap. To get rid of the negative 3 on the left-hand side, we add 3 on both sides. Negative 4 plus 3 is just negative 1. And, right, so let's write that down. Equals to negative 1. So all that's left is this g term and that j term. There's root 5 on both, just like this one. We can factor out the root 5. We get root 5 times g minus j is equal to negative 1. Alright, and last step is we're going to erase this, and then we're going to go from here to here. Dividing root 5 in this equation, we get f minus h is equal to negative 4 over root 5. Okay, and then last step before we can actually get to eliminating, g minus j, divide by root 5 on both sides, we get g minus j is equal to negative 1 over root 5. Okay, so that's it for this one. Alright, now we can start eliminating, and in fact this isn't all that bad. Adding, let's do f plus h and f minus h first. Adding these two equations on the left-hand side, the h's cancel out, you just get 2f is equal to 0 plus negative 4 over 5, which is still negative 4 over root 5. Okay, and from here, just divide 2 on both sides, we get f is equal to negative, dividing 4 by 2, you get just 2, and then the root 5 is still in the denominator. Down here, adding these two, same thing, right? You get 2g, j's cancel out. So 2g is equal to, and then you add 3 and negative 1 over 5. I would just keep them as separate numbers for now. So we get 3 minus 1 over root 5. This implies, dividing everything by 2, you get g is equal to 3 minus 1 over. Okay, but dividing by 2, now the 3 is divided by 2, and then now the 1 over root 5 is now 1 over 2 root 5. There you go. There's your first two coefficients. Right here and right there. Okay. All we need to do now is plug them. We don't even need these two equations anymore. So plugging f is equal to negative 2 over root 5. You get negative 2 over root 5 is plus h is equal to 0. Add 2 over root 5 on both sides. We just get h is equal to 2 over root 5. Here, we get g is equal to that. And then subtracting down both sides, let's just do this, right? So you get j is equal to, and then you get 3 minus whatever g is. So let's do that, like manually. So 3 minus 3 over 2 minus 1 over 2 root 5. Distributing the negatives. Oh, okay, well, don't do that yet. Let's just... distributing the negative sign, you get 3 minus 3 halves, and the negative into here is just plus 1 over 2 root 5. So evidently, all the arithmetic that is done is between these two terms. 3 minus 3 over 2 is just 3 over 2 again, plus 1 over 2 root 5. So this is essentially just the conjugate of this. Okay, so here we got 3 halves, but plus 1 over 2 root 5. Right, so that is it for these two. So we're actually done. So what we can do now is just rewrite this integral down here, which is, remember what we were originally trying to decompose, into two fractions, and plug in these coefficients. This is really cool. So let's do this. Let's do this down here. So this integral is the 1/4 coefficient stays. Now there's an integral. And in fact, let's break it into two, right? Just like we did before. The first one is over x squared minus phi x plus 1. And yeah, let's write in the coefficients. Fx plus g. F is that, so we get negative 2 over root 5 x plus g. G is that. So we get plus 3 halves minus 1 over 2 root 5. Integrate with respect to x. Next one, we have plus that. So the 1/4 coefficient is distributed. And then we have a denominator of this. X squared plus 1 over phi x plus 1. Okay, and on the top, we have hx, which is 2 over root 5 x plus j. J is plus 3 halves plus 1 over 2 root 5. close the integral with the differential that's multiplied in. There you go. That's whatever you're dealing with now. So I'm going to erase all of this. Being careful not to erase anything that we just came up with. Okay, now we have two terms. We're going to work on these together simultaneously. We're going to work on both of these simultaneously. So here we have a common factor. No, not a common factor, but we can factor out something from the top. We can factor out, because it's a complex fraction, let's just multiply the top and the bottom both by by the least common multiple, which is just 2 root 5. So down here, if you multiply the top by that, you also have to multiply the bottom by that. So I'll bring this outside. So 4 times 2 root 5 is actually 8 root 5. And then integral. Okay, now the top, negative 2. In fact, we can just switch the polarity of all of these individual signs by factoring out a 2. By factoring out a negative, sorry. So we'll have a negative out here. So this is no longer negative. The root 5 cancels with the root 5. The root 5 cancels with the root 5, right? And then we multiplied into 2 as well, so we have to multiply that by 2 as well. In the end, we get 4x plus, okay. So on top here, you get 3 over 2. When you multiply that by 2 root 5, the 2 and the 2 cancel, you just end up with a 3 times the root 5. So the 3 stays, but then now you're multiplying by a root 5. And the last one is probably the easiest one, since the denominator just cancels. So you just end up with the 1. And then the bottom stays the same. Vx plus 1 dx. Let's work on this next term. We do the exact same thing, just we don't factor out a negative here. So instead we just factor out a 2 root 5. Bring the 2 root 5 out. So there's another way to think about it. We bring the 2 root 5 in the denominator out into the denominator of the outside. So similar to the first time, we also get 1 over 8 root 5. And I think I'm going to be running out of room, but we're going to keep working on this. And the numbers here are all the same, right? Sorry, here we needed to do a pole change or a polarity change, so get minus and plus there. Okay, we can copy what we did here for this one, right? Since the numbers here are the same, we have 3 halves, 1 over 2 root 5, 1 over 2 root 5, then the 2 over root 5. So in fact, doing this, they're essentially equal, just like, but the only difference is the polarity of the coefficients on the inside are not. So we can just copy this down, but make everything positive, since it's already positive and we didn't factor out anything positive. So this would be 4x, and then plus 3 root 5, and then plus 1. And then this is over the denominator, which is x squared plus 1 over 5x plus 1. Close it off with multiplying the differential dx. There you go. This is simplified. Okay, now remember what we did when we had to be able to create this, right? Multiply both the top and the bottom by whatever coefficient necessary to make the top a derivative of the bottom. We can do the same here, since the top is just 1 degree less. If it's 1 degree less on the top, we try to take advantage of natural log. If it's 2 degrees less, then we have to do something else, like we did the partial fraction decomposition here. But here, we can easily do what we did to be able to achieve that. So here, the derivative of the bottom is just, let's erase all this partial fraction decomposition and just keep our 2 big boys down here. Right. Okay, so so let's make a note to ourselves. If we want the top to become the derivative of the bottom, we have to calculate the derivative of the bottom first. The bottom is just, the differential operator. Okay, but the derivative of the bottom is just, for this first fraction, would just be bring the 2 to the bottom, and then minus phi. But because the top is expressed in terms of, well, normal numbers and radicals, we can just write phi in terms of normal numbers and radicals. So negative 1 plus root 5 over 2. Similarly, for this other one, for the next fraction, right, and then this is equal to also 2x, but now this constant, this becomes just 1 over phi. 1 over phi is equal to negative 1 plus root 5 over 2. All right, so how do we get that? Well, pay attention to the term of highest degree, right? Here we have a 4x, here we have 2x. We want to make this 4x a 2x. How do we do that? Divide by 2. It's pretty simple. So, in fact, to divide the numerator by 2, you have to also divide the denominator by 2. Dividing 8 root 5 by 2, you get 4 root 5. Multiply by, this now becomes a 2x. And then, yeah, let's just divide by 2, and then we can work out how to split this up, how to split this guy up into that. All right, so negative 3 root 5 over 2 plus, well, this one's pretty funny, it's just 1 over 2. And the bottom stays like this. Alright, this second one, basically same thing, right? We still gotta divide 4x by 2 to get the 2x that we want. So, and that means the same change that we make to the denominator. Make this a 4 instead of an 8. Times root 5, integral. Okay. Numbers are the same, polarities are different, so we'll just copy it down from whatever we wrote there. Get 2x minus 3 root 5 over 2 plus 1 over 2. Okay, and then we have x squared plus 1 over phi, x plus 1 dx. Okay, so we'll get rid of this now. We're gonna work from the top down again. So this is what we're working with. We need to find some way to pull this number out of here and then this number out of here. So we notice that let's split this into two fractions. So here we have 2x, and then we have minus 1/2 minus root 5 over 2. Here we would make this 2x minus 1/2. But instead it would be a plus root 5 over 2. So just a conjugate, right? These are conjugates of each other. Okay. To be able to pull out a minus 1/2, that's common between both of these. Similarly, the plus 1/2 is also common between both of these. So to be able to pull out a minus 1/2, we would need to so we can write in, all right, you know what, let's do it like this. 2x. All right, let's write a minus 1/2 here. And then we can compensate to make this negative 1/2 that later. Next, we have to pay attention to this term right here. We want a negative root 5 over 2, but we have too many of them. In fact, we have 3 negative root 5 over 2s, if you think about it like that. So we can just have a negative root 5 over 2 here. Right. Okay, next up, we have to compensate. So, in fact, I'm gonna, if you want to think about it, if you want to add back whatever the hell you need to add back in the numerator here, you can still split that off as a different fraction and then split the integral. Okay, after splitting the integral, this coefficient needs to remain the same, so we get 1 minus 1 over 4 root 5. Okay, so to be able to compensate, to be able to get this number back to 1/2, you need to add 1. To be able to get this number back to negative 3 root 5 over 2, you need to subtract off 2 root 5 over 2, which is just minus root 5. The denominator would need to stay the same since you're essentially just splitting the fraction first, in which case the denominator stays the same. Now we need to do the same thing here. So this no equal sign, positive 1 over 4 root 5. Slightly different, I'm sorry, this wouldn't be negative, this would be a positive. Okay, so the 2x would stay. To be able to get the negative 1/2 from here, let's just write down a negative 1/2. And then we also want now we want a positive root 5 over 2. So we want plus root 5 over 2. Okay, so that would be our first fraction, and then we split the compensation into a different fraction. So this would be x squared, and then plus 1 over 5x plus 1 dx. Almost done. Almost. This can now be integrated, that can now be integrated, and we just have 2 more lone fractions with that look like that to deal with. So, anyways, splitting the fraction means the coefficient needs to be the same. No, I mean splitting the integral. So, now, this isn't supposed to be s, this would be a 5. Okay, inside of here, to be able to compensate for the 1/2, you would need to add 1 for this to go back to 1/2. So let's just add 1. For it to go from root 5 over 2 to 3 root 5 over 2, you need to add 2 root 5 over 2, which is just root 5. So you plus root 5 here. See, this row and this row are very similar. It's just that the polarity is like changed, so we can't do it. We can't combine like terms, which is kind of annoying, but makes the answer all the more satisfying. So, and the denominator would stay the same when you're splitting fraction, dx. Okay. Let's call this I3, and let's call this I4, right? Since you're already ready to integrate them. And by the way, at the very end, all you need to do is to add I1, I2, I3, I4, I5, I6, etc. together to create this original integral right here. Since we're just naming these terms that we split off, these variables, so we can just deal with these guys that need work, right? But since they're just being added on, we're like splitting this, making this bigger, and we give it more terms, right? There's more terms now. Just name each of the terms a different I value, well, I with the different subscript, add them back together, and you get the original one. So, we can let this one right here, so we have negative 1 over 4 root 5 times integral of that. On top you have 2x, and then recall that if you just factor out the negative, you get negative 1 plus root 5 over 2. That's just negative 5. And then copy the denominator. Dx equal to I3. Then, very similarly, we want to do the same thing to here. We want to let 1 over 4 root 5 times the integral of this. So this, we already said this is just combine the fraction, you get negative 1 plus root 5 all over 2. So, and that is equal to the reciprocal of phi. So here you get 2x, and then plus the reciprocal of phi, 1 over phi, over 2, all over x squared plus 1 over phi x plus 1 dx. Okay, and we call this I4. Okay, so we're done with that. Now we have 2 more bad boys to deal with. And by the way, since they're just terms, this and that, all they do is add together. Okay. And in fact, here, because these are also technically additive, since you can switch the order of addition, you could have just combined these. Do I want to? Probably not. Yeah, we'll deal with that later. Okay. So anyways, we have our new integral that we're trying to find some way to make it so that we can find an antiderivative. We have that. And this part is the a very difficult part to wrap your head around, but and then you add 1 over 4 root 5 times the integral of 1 plus root 5 all over x squared plus 1 over 5x plus 1 dx. Okay. Now, there should be enough room for us to simplify that to these guys to a point where we can just take the derivative. Okay, so, in fact, you notice that the top is just a constant. You're able to bring, sorry, I'm opening the window, but you're able to bring that constant outside of the integral using the linearity of the integral. So let's do that first, right? It'll make it look a lot simpler because the top is just a constant. We don't need to deal with that. So when we bring this outside, we can use a negative sign to reverse the order of subtraction. So we get 5 minus root 1 over 4 root 5. And then we do something cool. I'm gonna guess. Oh, and sorry, this is no longer negative since you reverse the order of subtraction. Okay, in fact, what we can do here is, okay, let's just take a look at this guy first, right? So we can actually write this in terms of something simpler. So, okay, let's go back to what we originally had. We had a negative, and then we would have just brought. Okay, no, that's not what we're trying to do. Let's rewrite this, real quickly. Plus root 5 over 4 root 5. If the numerator looks familiar, it's because it's the numerator of the representation of phi, right? So instead, it's negative 1 plus root 5 all over 2 times 2, right? And then you do 4 over root 5. Once again, and now this is no longer phi, right? That's the wrong number. This is, in fact, 1 over phi. So there's a negative 1 over phi. And then this 2 and the 4 cancel to make 2 root 5 in the denominator. Sorry, this is not negative. This is just normal. And finally, because we have this guy on top, we can just multiply both the top and the bottom by phi to cancel that out. We're left with the 1 on top and a phi 2 root 5 on the bottom, which is pretty interesting. In fact, I think it would be actually expressed as 2 phi root 5. So that would be our coefficient for this. So let's replace this with 1 over 2 phi root 5. Okay, and then let's just rewrite this as just having a 1 in the numerator. And in fact, for right now, I'm gonna rewrite this phi in terms of its expression in terms of numbers, because we're gonna be completing the square in a second. Okay, but regardless, let's do that. So we're gonna replace this with 1 plus root 5 over 2 x plus 1, and then dx. Is there a better way to do this? Okay, so we have that. Now we have to solve for, we have to bring this outside and solve for the coefficient. So this would be 1 plus 5 over 4 times root 5, right? Divide both the top and the bottom by 2, or multiply the top by 2 and simultaneously divide it by 2. Then what you get is, this is just normal phi, and the 2 cancels out with the 4, you just get 2 root 5. So yeah, that's how that works. Alright, so you would add, and also notice this looks a lot nicer now because we managed to make the polarity of both of the coefficients positive. Anyways, we get phi over 2 root 5 here times the integral. Okay, integral on the inside, the integrand, the top becomes 1, and then we want to re-express. Sorry, I would actually write that as in red, and we want to re-express the bottom algebraically. So 1 over 5 is just negative 1 plus root 5 over 2, and then multiply by x, and then add 1, and then close the integral. Okay, so we got the top sorted out. Now just take a look at the bottom. So in the bottom here, we want to complete the square for this value right there. It seems kind of intimidating, but to complete the square for that, you can complete the square for anything. All I need to do is take the absolute, it's just to take, no, not absolute value, but the coefficient of x, right? So the coefficient of x is negative 1 plus root 5 over 2. Divide it by 2, and then square all of it, right? And then that's the number you need to add to the end. So now we can do the math. Dividing this by 2. Okay, so dividing this by 2, the denominators just multiply. You get negative 1 plus root 5 over 4, right? Squared. Now to square this guy, you would get, let's work out the top squared first. 1 plus root 5 squared. 1 plus root 5 squared. So if you use what we typically use, which is 1 squared is just 1, plus 2 times 1 times 5, which is just 2 root 5. And then root 5 squared is just 5. Right. Simplify this by combining those, you get 6 plus 2 root 5. Factor out of 2, you get 3 plus root 5. Okay. So yeah. In fact, what we get is on the top you get 2 times that. So yeah, let's write it out. 2 times 3 plus root 5, right? That's this guy squared. And the bottom, 4 squared is 16. And this is also equal to, after canceling the 2 and part of the 16, we get 3 plus root 5 over 8. Alright, and that's how we complete the square for the first one. So let's keep that number right there so we can refer back to it. Let's just write that down. So we have 1 over 2 phi times root 5. Integral of 1 over x squared. We can now re-express this as phi, right? Because all I want to do that for was to be able to solve for the value that completes the square. So this is back to minus phi x, and then plus that, right? To be able to complete the square. Okay, and then now you want to subtract it again. So what's remaining is the 1, and then the minus this guy. So let's compute that. You get 1 minus 3 plus root 5 over 8. So you get 1 minus 3 over 8 minus root 5 over 8, right? Because the negative sign distributes, you can split the fraction. 1 minus 3 over 8 is just 5 over 8. And then you can just combine the fractions since they're both over 8. You get 5 minus root 5 over 8. So you want to break this into 5 minus root 5 over 8. And to check that these add back up to 1, since that's basically where these two both came from, 1. 3 plus 5 over 8 is just 1. And then positive root 5, negative root 5 over 8, they both cancel each other out. I hope everything is still recording. I'm going to check the battery life on these devices. Yeah, we're going fine. Okay, that's how you complete the square for the first one. Now let's work on the second one. So the second one, coefficient stays, just like before, 2 root 5. Integral. So, just like before, we can now re-express this red part in terms of phi because we're done with actually, yeah, okay, let's solve to complete the square first. To complete the square for this guy, we want to do the same thing we did earlier, where we negative 1 plus root 5 over 2, right? We have to divide it by 2 first, and then square the whole thing. Let's distribute the square, just to, well, actually, no, it's probably easier just to divide that first. So now you're left with negative 1 plus root 5 squared. And then on the bottom, you have 2 divided by 2 is 4. 4 squared is 16. Okay, so what's that? To be able to compute that, we do the first one squared, which gives you 1. And then 2 times the first one times the second one, which is negative 2 root 5. And then just the second one squared, which is 5 over 16. Okay, so then combine 1 and 5, you get 6. 6 minus 2 root 5 over 16. And then dividing both the top and the bottom by 2, you get 3 minus root 5 over 8. Okay, and similar to this, we also have to subtract 1 minus that, because we have this 1 here. If we're adding it, we also have to subtract it. So we add this guy over 8. Okay, and then we want to subtract a value to be able to get, or just split 1 into this and another fraction. Another way you can look at it, as we did earlier, there would still be a plus 1 down here, and then you want to subtract this guy to cancel it out. So in essence, you want to do 1 minus that. 3 minus root 5 over 2. Okay, you can split the fraction by distributing the negative sign. You get minus 3 over 2 plus root 5 over 2. 1 minus 3 over 2 is just, you get 2 over 2 minus 3 over 2. You get negative 1/2 plus root 5 over 2. Am I right? Is this right? Yeah, it looks right. What? Seems kind of... Alright, because this is just the value that completes the square here. And it doesn't make sense if you add this either, since what you're doing is negative 1 plus root 5 over 2, right? If you were to add this back, the negative 1 over 2 and 3 over 8, do they cancel? Oh, sorry. There's 8 in the denominator here. Okay, that's why. Let's get rid of this. But yeah, there's an 8 in the denominator. Let's rewrite that as 8. There's a fly. Okay, so now we split the fraction. So you get 1 minus 3 over 8 plus root 5 over 8. 1 minus 3 over 8 is just 5 over 8. Combine the fraction, you get 5 plus root 5 over 8. So, adding this back, and you can do the number math. You can just do the arithmetic here to make sure that it works. And it does indeed work. Oh, my black pen is running out quick. DX. Alright, that's the square completed. Alright, now what you notice is this, right, and that are both perfect square trinomials. So what you can do is rewrite them as perfect square trinomials. Coefficient stays the same. Now on the bottom, we have x. Here it would be minus 5 over 2 squared. And then since we want a sum of squares in the bottom, we also need to be able to express this as something squared. And to do that, take the square root of both the top and the bottom, right? Square root of the top is just, we can't really simplify the roots. So you do root 5 minus nested root in here. And then square root of 8 is just 2 root 2. Square this guy. Okay. And then we've got this one. And also remember to close this first one with a dx. But we got 5 over 2 root 5 integral. And this is cool. So find the denominator here and find numerator here. Regardless, this is a perfect square trinomial. We write it as a binomial squared. You would get x plus 1 over 2 phi. Yeah, squared. let's see if that's like the best way to, I guess so, because that's what I did in my notes. And then once again, notice that this is almost the exact same value. It's just that there's a negative sign in here that's not in here, but that doesn't change anything, right? It's still just this, but instead of negative, it's a positive. So let's just copy that down. Root 5 plus root 5. Root 5 plus root 5. 2 root 2 squared. 1 in the numerator, dx. Then, we can call this I5 and that I6. Then add it all together and you're done. So in fact, what I'm going to do is, since we know that these four added together gives you like the remaining part of this integral right here, we're going to just write each of these down individually, right? So I1 is, we're going to integrate now. Since you can see that we can just make a substitution here. Since it's sum of squares, we get inverse tangent. Okay, here. So let's get started. We get this is, now we can officially draw an equal sign that equates this to whatever we're going to write here. So this is equal to 1/5 integral of 1 over x plus 1 dx. And then you'd subtract 1 over 20 integral of, the top is 4x cubed minus 3x squared plus 2x minus 1. Then the bottom is x to the 4th minus x cubed. Wait, minus x cubed. Yeah, that makes sense actually. Does it? Yeah, it does. I'm thinking about this wrong. Plus x squared minus x plus 1 dx. Okay, so that's I2. Now I3 is negative 1 over 4 root 5. And here, the top is the derivative of the bottom. So we get 2x minus 5. And the quadratic on the bottom is x squared minus 5x plus 1 dx. Alright, and then now we have I4 that's also added on. So we get plus, the coefficient is 1 over 4 root 5. Then this integral, similar to this one, the top is the derivative of the bottom, right? So we get 2 plus 1 over 5 over x squared plus 1 over 5x plus 1 dx. Okay, I'm going to scroll this down in the bottom below this, since there's really no easy way to get that to look very nice. Like up here, you express this, no complex fraction at all except for that, but that's an exception. Here, it's a little messier, so I'm going to write it down in the next line. I'm going to add this, right? So now you're adding 1 over 2 phi root 5 times integral of, I'm going to give me a lot of room in the denominator. Yeah, 1 over x minus phi over 2 squared plus root of 5 minus root 5 over 2 root 2 squared dx. Next term, we add the phi's on top over 2 root 5 integral of that. You just have to copy that down. So we have x plus 1 over 2 phi squared, right? Plus root 5, this line is plus root 5 over 2 root 2 squared. So 1 dx. Alright. So all of our extra work is done. Now what you're left with is that, but written as a sum of integrals that we can just directly make a substitution for and then immediately integrate afterwards. So here's how we're going to do this. I'm going to use, what if we use Greek letters for substitutions? So we need to make 6 substitutions. 1, 2, 3, 4, 5, 6. Okay. So first substitution, let's use alpha. Let alpha equal to x plus 1. Here, this implies that d alpha gives you just dx. Right. So, yeah, all right. We let, in fact, I'm going to put my black pen, I'm going to cap it, since if I don't cap it, it's going to die, and we're also not going to be using it much when we're writing down all of the substitutions, but yeah. Okay, second one, let that quartic polynomial, x to the 4th minus x cubed plus x squared minus x plus 1 equal to beta. Okay, I wrote that first, but regardless, d beta is equal to that. So 4x cubed minus 3x squared plus 2x minus 1 dx. Right. Okay, next substitution is this in here. So we would let this quadratic on the bottom, since the top is the derivative of the bottom, let gamma equal to the quadratic on the bottom, x minus 1, no, plus 1, and then differentiate gamma, just be 2x minus 5 dx. Notice that that is the top. All right, here we want to let delta equal to x squared plus 1 over 5x plus 1. Right, and then this implies that d delta would be equal to, d delta, that's kind of weird, but anyways, d delta would be equal to the numerator. We get 2x plus 1 over 5 times dx. All right, and then here we would want whatever this linear term containing x to be equal to for us to make the substitution, since u squared plus that squared. After delta is epsilon, let epsilon equal to x minus 5 over 2. Differentiating epsilon, d epsilon is equal to just dx. Okay, and then final one, it would be that one. You would want the next one is zeta, I think. Right. That zeta. Oh, I haven't ever like written out a zeta before, but I think it looks like that. Close enough. So there's it's this. Let zeta equal to that, x plus 1 over 2 phi. Then therefore I'm struggling to draw this guy. d zeta is equal to dx. Let's rewrite all of this down here. So, therefore, almost done. This top one, okay? We keep the coefficient, but now 1 times dx is just d alpha, so we write d alpha. And the bottom, as you can see, is just alpha. Okay, next one is minus 1 over 20 times integral of, you can see the top is just d beta, and the bottom is just beta. Alright, and then this one right here. So gamma, right, the bottom is gamma, the top is just d gamma, and the coefficient is 1 over 4 root 5. So we get d gamma over gamma. Okay, and then this one, very similar. Bottom is, the top is the derivative of the bottom. So we end up getting, no, sorry, not an equal sign. Just ate fucking fly. Anyways, 1 over 4 times root 5 times the integral of the top is d delta, as you can see, the bottom is delta, so we write d delta over delta. Okay, and then now we have the inverse tangent, guys. They're gonna take up quite a lot of space, but the coefficient stays the same. We have 1 over 2 phi root 5, and then integral. So the top stays 1, bottom, I'm going to write the du on top actually, but this guy is just epsilon. So we have epsilon squared plus then that value, which is root 5 minus root 5 over 2 root 2 squared. Okay, and then since 1 times dx is just d epsilon, I'll just write d epsilon on top to save space. Okay, final term, we have this. Another inverse tangent, we said this is zeta, right? So coefficient stays the same, it's just phi over 2 root 5. And then 1 over, well, I'm going to write d zeta on top, as I did for epsilon. We get zeta squared plus, and then this boy, which is root 5 plus root 5 over 2 root 2 all squared. Then you just have a d zeta on top. That is it. That is our integral expressed as a sum. That's our integral expressed as a sum of integrals with substitutions made. So here I'm gonna go straight to the antiderivative, and I'm gonna sit down for this part because it's getting kind of low. But okay, so 1/5. The coefficient stays, of course. We have a natural log of alpha. And alpha is really just x plus 1. In this case, the absolute value is necessary, but not for the next one, as we will see. 1 over 20, natural log of, since it's d beta over beta, and beta is just that. And because there's no roots for that, it is always positive. We don't need absolute value bars. Okay, I just hit 2 hours. Anyways, next we have this one right here. So we got 1 over 4 root 5, and then a natural log of gamma, which is also irreducible and always positive. So therefore, we are able to omit the absolute value signs. We get x squared minus phi x plus 1. Okay. Then next term, d delta over delta, we have just natural log of delta along with the coefficient. So we got plus 1 over 4 root 5 times the natural log of delta. Delta is just that. So we have x squared plus 1 over phi x plus 1. Okay. I'm going to go to the next row. Okay, now it gets kind of complex, but just take a minute to think about it, right? Next we have this term, the epsilon. So the coefficient stays. We got 1 over 2 phi root 5. Okay, so how inverse tangent works is the coefficient becomes the reciprocal of whatever is squared in here. So it would be 2 root 2, sorry, not root 5, 2 root 2 of this nested root right here, root 5 minus root 5. Okay, and then the inverse tangent function appears. Then you want epsilon on top, and then you're seeing on the bottom. So basically multiply epsilon by the reciprocal of that. We'll do that real quick. So we'll first multiply the reciprocal, and then epsilon. Epsilon is that. We have x minus phi over 2. Okay, finally, and actually we're actually missing one parentheses. We have the other inverse tangent right here, right? So the coefficient would stay the same. We add phi over 2 root 5, and then multiply by the integral of that. So, as I said earlier, take the reciprocal of that, put it on the outside, 2 root 2, divided by nested root of 5 minus root 5. Okay, then we have the inverse tangent popping up. Okay, and then we have multiply the reciprocal again. So you have 2 root 2 over root 5 minus root 5. This is extremely tedious, but then we multiply by zeta. Zeta is just x plus that. You have x plus 1 over 2 phi. Close that, close that, close that, and that is our antiderivative. However, there's some simplification to be made, so all I'll do is I'll copy all these terms down again, right? No big deal. We've done this like so many times at this point. Okay, so I'll copy these four down, and then I'll get back to you about the tangent ones. So we have 1/5 natural log of absolute value of x plus 1 minus 1 over 20 times natural log of x to the 4th minus x cubed plus x squared minus x plus 1. Then you would add 1 over 4 root 5 of the natural log of x squared minus phi x plus 1. Finally, the last term is that we don't need to manipulate yet, is this one, is 1 over 4 root 5 of natural log of x squared plus 1 over phi x plus 1. Okay, let me check that this is still recording since we're approaching the end, and this is very high stakes. If this thing just shuts off, womp womp. Okay, finally, we want to manipulate this. So on the outside, we can see that root 5 kind of just multiplies in. You can't really combine those at all. And the 2 cancels with the 2. So you're left with root 2 on top, and then 2 cancels with the 2. So you're left with phi times root 5 times nested root of 5 minus root 5 on the bottom. And then there's a root 2 on top. Inverse tangent of... Okay, so for this one, you can distribute it. You have this times x, which you can't really do anything with. So we just get that, right, minus root 5 times x. And then you would want to subtract off this times that. The 2's cancel, nothing else really does. So you want to subtract you would do phi times root 2 over that. So which is root 5 minus root 5, all nested. All right. Final term. Here the 2 on the bottom cancels the 2 on the top, similar to before, and then now the phi and the root 2 are multiplied together in the numerator. So here we have phi root 2. Then the root 5 times that nested root is still in the denominator, root 5 plus root 5. Okay, dude, I swear, I can't draw this right. Okay, then we multiply by the inverse tangent of that, right? So here, you would also distribute this number with x first. So I'm going to do that first. So we get 2 root 2 over root 5 plus root 5. Did I write minus here? This is supposed to be a plus, right? Yeah, okay. And then times x. After distributing, you get that the 2 cancels with the 2, right? So now you're left with a positive. I would write the 5 first in the denominator, and then since the 2's cancel, you're just left with this nested root 5 plus root 5. And then in the numerator, since the 2's cancel, you just have a root 2 times 1. So you're left with a root 2 in the numerator. And that's it. This is the antiderivative of that little boy up there. All that's left now is just to add the arbitrary constant of integration. Right, we denote as c. We're done. Everything done. It all looks good. Right. Yep. That's it. That's the antiderivative. If you graph, and in fact, if you graph, I'm gonna box the answer first, because this is very cool. Right. Okay, I'm gonna count my markers. So, one cool thing about this is that if you graph this and that, like, just add bounds, like, say, if you're in decimals, you'd have to add bounds, you'd just say from 0 to x, and then replace the x's in the integrand with t, and with respect to t, they would actually give return the same graph. However, this is shifted off by a constant, and it's a constant that, not completely sure about. It's a weird number. Let me pull it up. So the constant is, it is around 0.10207653. So if you want me to write that out, and if anyone can figure out what that constant, what that constant would be in its exact form, I'll write that out. It's 0.102, right? 0.102 07653. 07653. And then it's irrational, right? If anyone can tell me the exact form of this number, by the way, there's a decimal point there, that would be highly, highly appreciated. But yeah, this constant, for the graphs to look the same, you would have to, instead of adding just c, you would have to add that, right? That's the beauty of c, it's because this can be shifted out by a constant, you just wouldn't know. But yeah, it's approximately that. Alright, that's it. That is the integral of 1 over 1 plus x to the 5th. And I'm going to read out the antiderivative. The antiderivative, I'm not even going to try. It's just that, right? Keep in mind that phi is equal to the golden ratio, 1.618. You can also express it in its exact form, 1 plus root 5 over 2. All over 2, right? Yeah, that's it. That's the antiderivative of that boy right there.